Infinity, Taylor, and the Maclaurin series. Taylor and Maclaurin series is good for representing a function fx, and this is the formula with a remainder. And if a is equal to 0, it's called Maclaurin series. And if the remainder is 0, then your function can be represented by this equation. And this is how you calculate the coefficient by differentiating and then put x to a and get the equation. These are some other representation. These fx expanded at point A, and these are infinity series, or you can use x plus h, and you only have the x, you don't have the a in here. And some other representation like this, and Maclaurin is a equal to 0. These are some other representation form, and these are remainder. Remainder are two kind of remainder, depend on the choice of reference function. I will show you later. Okay, so these are Taylor series, and this is how you find coefficient, and the remainder is Rn. And so to find the Rn, remainder of the Rn, you can need to use the extended mean value theory, and you can pick a function like this, and you get the Lagrange. A different choice of this function will give you another form. So let's see the mean value theorem of differentiation. Basically, what it means is you actually can find a tangent in between these 2 points. And the extend mean value theory is these two difference can equal to the differentiation, first differentiation. Okay, using this is how you derive the remainder. If you choose auxiliary function differently, you get a Cauchy remainder form, and remainder in Maclaurin series is like this. These are the example using the trigonometry function sin x, and you can see the value here and cosine x here, and both remainder tend to be 0 as m equal to infinity here. So basically, and you can just modify both and do some manipulation and get other expansion, Taylor expansion. These are the one of the example, e to the 3x about x equal to 0, and these are something that you can take a look. These are some of the list of the sine, cosine, sine square, sine cube, x, and x for exponential function or hyperbolic function, because the exponential is differential is equal to itself, so they are all 1, so easily you get the expression. And so the hyperbolic function is this. You also can get it from exponential function. These are some pronunciation. Instead of saying the hyperbolic sign, you can say shin. Okay, and hyperbolic tangent can be equal to hyperbolic sine divided by hyperbolic cosine, and you can get all these expression here. For logarithm, and you can see that differentiate the logarithm function is like this, and so you can get the Taylor expansion. These are some other example of logarithm function. And if you use 1 theta equal to x, and you get another Taylor expansion for different function. And for you can also using Taylor expansion to represent the binomial theory. If in binomial theory, if m is not a positive integer, then you can expand this way. And these are some example. And if it is a negative integer, you also can expand it like this. And these are some example of arcsine, the inverse trigonometric function and hyperbolic function. First derivative are simply algebraic function. So you actually can differentiate it like this and get the function Taylor expansion. These are example of binomial theory, and these are example of exponential and logarithm function, trigonometry function, hyperbolic function, some other miscellaneous series. These show you the binomial, exponential, trigonometry, and arctangent, and exponential. And some special theory, like sine integer, you can integrate the term by term to get the expansion. Like the logarithm integral. Okay, so these are the example of the application of Taylor theory. You can use to calculate the exponential and using this equation, and it's actually easier to calculate exponential if you using this way. Okay, and another example is calculate pi. You can use this equation to calculate pi. And use for binomial